My name's Steve, and I'm going to talk to you about geospatial data display with OpenGL ES for iOS. So let's get started. So first I'm going to go over what I'm going to go over in this talk, which is what I'm going over now. And then I'll talk a little bit about what geospatial means and how it relates to display. Then I'll talk a little bit about OpenGL ES and particularly the differences between version 1.1 and 2.0. Then we'll dive into some code, which will show a simple example using OpenGL ES on iOS. After that, we'll talk a little bit about resources you can use to get up to speed. And then we'll talk about speed. After that, we'll talk about toolkits, some that are open source and other toolkits as well. And then we'll go into dynamic geometry. We'll show an example where we actually change things. And last but not least, we'll talk about OpenGL ES image processing, another use you can make of OpenGL ES. And then we'll wrap up with a quick spheres and texture example. All right, let's talk about me. So I'm an iOS consultant, a software engineer, and I specialize in 3D stuff. And I've been working on iOS for a few years now, mostly doing 3D interactive graphics. I make a toolkit, which I'll talk about shortly, and I've been using GL for years and years. I even go back all the way to IrisGL, so a long time. So the toolkit I make is called Whirly Globe Maply, and the Whirly Globe portion is an interactive 3D globe, and the Maply portion is a 2D flat map. They're both Apache 2.0 licensed, so you're pretty free to use them in commercial tools. They rely heavily on OpenGL ES, and they implement a lot of different features, some of which we'll see. So let's talk briefly about what geospatial is, and here's the definition from Wikipedia, and it's kind of long, a little bit boring, and it uses words like geographic information systems and geomatics, and you'll see a lot of geo in it. And it's it's a good definition, but in its own way, it's kind of daunting. And that's kind of what geospatial is. And there's definitely a bit of a ramp up to kind of get your head around it. But it actually can be simpler than that, particularly the display side. So I would say, for our purposes here, geospatial is flat maps. Geospatial is 3D maps, and geospatial is also interactive globes. Those are all good examples of geospatial data display. But most of all, I think geospatial is just plain fun. It's really interesting to display this data, see it in an interactive way, and let users see what users can do with it, see how they play with it, what they do with it, that sort of thing. So let's take a quick look at an app which makes heavy use of OpenGL and geospatial called Stratologica. So this is an example that uses a lot of OpenGL ES and also just does geospatial data display. It's an app called Stratologica, and it is used by teachers for essentially for students to do history lessons or current affairs or geography or what have you. So it's a globe, and they've got these custom skins on top of the globe. And you see as you zoom in, it'll load in higher resolution skin. Zoom out, it'll get rid of it, and it's just generally zippy fast. It's running at about 30 frames a second, and it's a great example of what you can do with OpenGL ES. So I'll show you a couple of things here. So one are these presentations. So you can put together a presentation to explain current affairs or what have you. And one of my favorites is this plate tectonics example where they're showing how the plates are oriented on the Earth. Here you can see they've outlined the plates with lines and names on top of those as well, and how that relates to the large Japanese earthquake of a few years ago. So in addition to the lines and other features in these labels, we've also got pop-ups. So for example, you can have these pins like over here that you can tap on, get some information about a feature, or run a video, or do all sorts of things. And if you zoom in far enough, you'll switch from this kind of abstract display here to Bing satellite imagery. So you can actually play around with that as well. So, and again, all of this is OpenGL ES, and much of it's based on the Whirly Globe Maply toolkit. And of course, it's geospatial display. So oh, before I forget, there's one more interesting thing which I always like to show off. You can also edit. So let's drop down an icon here. And we can move it around and change its orientation. There we go. And that's actually stuck to the surface of the globe, which is harder than it sounds. And my favorite feature, actually, you can draw on things as well. And again, that's stuck to the surface. So, you know, it's the same kind of thing we're showing in the tutorial, but obviously more advanced. So, definitely worth a look, called Stratalogica, and they have a free mode if you want to check it out. Okay, having looked at a quick example there, let's talk more about the underlying technology. OpenGL ES is the toolkit that graphics chips vendors and mobile vendors use to do 3D and 2D graphics. And here's the description from the standards body, Chronos. Basically, it's a full function API for doing 2D and 3D, and it's a lot simpler than its more complex cousin OpenGL on the desktop. But it works fairly well. So you'll encounter a couple of different versions of OpenGL ES on iOS. One is the older version, 1.1, and that's a subset of 2.0 functionality. It's got what's known as a fixed function pipeline, so that means a lot of the functionality is kind of pre-baked. Like you can have a certain number of lights, you can have a certain number of effects, that sort of thing. It's not as flexible as 2.0, but in a lot of ways, if you're doing 3D, it's more intuitive. However, this version is old. There's a lot of missing functionality, particularly shaders. And if you're looking at an open source toolkit or any other toolkit that uses OpenGL, you should be a little suspicious of any toolkit that's still using only 1.1. And I wouldn't buy any books that focus exclusively on 1.1 either. So 2.0 is the newer, OpenGL ES 2.0 is the newer toolkit, and it's simpler in many ways. It really matches how the hardware thinks a lot better. It's got a lot less clutter, like lighting handling and all the state handling that was in 1.1. And it's got this notion of shaders, which OpenGL on the desktop has had for a very long time. Basically little programs that you can execute on your triangles and basically your vertices and your pixels. And that lets you solve an enormous number of really complex problems and also some really mundane ones in a really simple fashion. But OpenGL ES is complex in other ways. Because it matches how the hardware thinks, it's not terribly intuitive. And there's less state handling. If you needed that lighting, then it's going to be a little annoying that it's gone in 2.0. One other big advantage to OpenGL ES 2.0 is that it matches WebGL. And WebGL, and again, here's the definition from Chronos, is a cross-platform toolkit that people are integrating into their browsers. So if you learn OpenGL ES 2.0, then you'll have a foot up on WebGL, and that would be nice if you ever feel the urge to move to the web. Obviously, you still have to do JavaScript programming, but this gives you kind of an advantage because a lot of the algorithms will map over to WebGL. All right, let's take a look at a fairly simple OpenGL ES app example here. So here I've got an app which you can find on GitHub if you just follow the URLs. And its purpose is to display a single cube. And there we go. So it's basically drawing a single cube using OpenGL ES. And this is adapted from the template you get if you tell Xcode that you're creating a game. It just gives you an example app which you can rip the guts out of and go to town. So what I did here is I took out a lot of the extra complexity. So we're just using GLKit and we're just drawing the one cube and we're not doing much else. And with that, I'm going to illustrate a few things that I find important. So let's take a look at the actual source. And this will be the longest single chunk of source code that we'll look at, and this will go on for a minute, but after that we'll just kind of build on it. So again, you create this example with Xcode, and it'll give you, among other things, a view controller. And the view controller is really the important part. When it comes up, it creates the geometry, it starts, and then it starts drawing it, and so on and so forth. So the view controller is where everything happens. So let's start with that view controller. All right, so what do we got here? Well, we've got, the first thing to look at is the view did load. We've got a context. We're creating an EA-GL context, and this is essentially where GL will do its thing. So there's one, usually not exactly per thread, but there's one associated with a thread, and any GL calls you make in that thread are going to go into this context. So we create a context, and we keep it around. And then the next thing we do is we we set up this GL objects array, which is something that I set up for this example, and then we call setupGL. And let's look at that setupGL call. Okay, so for setupGL, it's pretty simple. Basically, we're creating a GLK base effect. Well, first thing I should say is we're setting that context we created as the current context. So now that means on the main thread right now, this is where we're going to be sending our GL calls. Then we set up an effect, and the effect is just this GLK effect is basically doing the lighting and handling the matrix math for us. It's I'm not going to get into it too much because there's plenty of documentation on this stuff. Then we enable depth testing, which basically means we're drawing in ZBuffer mode. And then we call setup single cube. And all setup single cube is doing, if you look at that, is it's setting up a cube at the origin with a size of 0.75. And then it hands that over to what's known as a flexi vertex buffer. And that's just an object I created for this tutorial. And I'll go into that in more detail. Basically, all it is a NS mutable data. It's a mutable data object that you can just kind of tack vertices on the end of. So it's just kind of convenience. I like to do that when I'm building up geometry, is just have flexible NS data objects, which I can just add data to. So once it's created that flexi vertex buffer, it asks it to create a SimpleGL object, which again we'll go into in more detail, and then it adds it to an array of GL objects, which we'll use in a second. So teardown's pretty straightforward. We're setting that context, and then we're deleting all those objects, and then we kind of clear out the array and so on and so forth. And then there are two important routines here for the GLK view and view controller delegate. So one is an update, and basically it doesn't really have much to do with drawing, but what they're assuming in GLKit is that you're going to be changing your geometry over time. Like in our case, we're doing that rotation with a cube. So that's all this is doing here. Basically, it sets up a bunch of matrices to figure out that rotation, place things, and then it updates itself. We won't go into that in much detail. This is the important one here, this draw and rect call. This is where we're actually drawing. So we clear the background buffer, and then we iterate over those GL objects. And I'll get to why there's a synchronized in a later example. That what that's doing is that's synchronizing on the GL objects. It's basically like a mutex. But we're iterating over the GL objects, and we're binding them and then drawing them. And you notice there's that call to make vertex array, and I'll explain what vertex arrays are in a bit. There's always kind of this big cliff to climb when you first start doing OpenGL, so there's a lot of objects here. So we bind the vertex array, we set up the effect, and all that's doing is basically providing information to our shaders, and then we draw. And this is where the rubber really hits the road, is we're drawing triangles, and we're drawing some number of them. That's what num vertices is. So with a draw arrays call, and with triangle set, basically you're passing in 3 times the number of triangles in vertices. So if I've got 30 vertices, that means I end up drawing 10 triangles. So it's a very simple call. That's why we're using it here. Okay, so that's the view controller. Let's look at a couple of those objects. So one that I talked about was the flexi vertex buffer. And this is hiding a lot of the complexity of building up whole lists of vertices. So here's the header file. And you'll see that basically, again, looking kind of near the bottom, all it really is an NS mutable data object. So we're just keeping track of the vertices as raw data, which we can make use of later. And we'll also keep track of the vertex size, because you can have different data in vertices. If you think vertex, you might think of an X and Y and Z, but there's also texture coordinates and colors and other texture coordinates and more texture coordinates and whatever else you want to pass into it. Vertices are actually very flexible in OpenGL ES. So you keep track of how big the vertex is, which GL is going to want to know, and how many vertices you're going to be drawing as well. So let's look at the actual object itself. Okay, so the first thing to notice in this flexi vertex buffer is that it's got this kind of static G cube vertex data, and this looks horrendous, but all it really is just a cube. It's the positions for each of the 6 faces and all their vertices and all the normals to go with them. And this is just stolen from the template you get if you create an Xcode game project. So don't worry about that too much. We're just going to copy those out. All right, so the important thing here is this add cube. That's the one we're calling. So we're going to add a cube at that location, size to the given size. So we work our way through all the vertices, and basically we just append them to the end of our buffer. That's really all there is to it. And then we also keep track of what our vertex size is. We know it's 24 because there's 3 floats for the position and 3 floats for the normal. And then we also were adding 36 vertices, so we keep track of that as well. Now the next thing we're doing here is a little more complex. So once we've built up this buffer containing our cube, we're going to need to tell GL about it. And that's what this is doing. So the first thing we do is we create a buffer. So now GL wants to think in terms of buffers. It doesn't really care that you're drawing a cube or 2 triangles or a rotating teddy bear. All it really cares about are these buffers. So we create a vertex buffer here. We bind it. That means it's the current one to which all the next set of calls are going to refer to. And then we put data in it. That's what that GL buffer data is doing. It's saying I want to put my vertices, which that's just an NS data object, and here's the data and here's a given size, and I want to put them into this buffer. And I'm also going to tell you that I'm not going to mess with the buffer. That's what the GL static draw is. And that's just a hint. So that's what the GL buffer does. It copies all that data over to GL, and now GL has a reference to it. That's the vertex buffer, and you can make use of it later on. So that's basically what the second part here is doing, is creating a simple GL object, which I'll show you in a minute, and that is encapsulating the vertex buffer and keeping track of other information we'll need, such as the vertex size and the number of vertices. And this is basically just information we'll pass to GL when we want to draw. All right, so let's take a quick look at the SimpleGL object. Okay, as its name implies, it's very simple. It contains a vertex buffer, which is again the reference that GL needs to access it, and then a vertex array, which I'll explain shortly, number of vertices, and the vertex size, which GL will want later. All right, so let's take a quick look, and unfortunately this is a lot to take in at once. So GL wants to refer to things as buffers. We could do that all the time, but in addition to that, just the buffer, it needs to know where in a given vertex its information is. So if you've got a vertex that has XYZ for the location, plus a normal, so that's 3 more floats, plus texture coordinates, plus a color, that could be in any order, and you have to tell GL what the order is and where it is. And that's what this is doing. Now, what they recognized was that that was a lot of state to retransmit all the time. So instead of making you reset that each time you want to draw, they added this construct called a vertex array, and it's an extension to GL. And we're using these here. Apple really likes them, so we're using them. Basically, you just create one. That's the GL gen vertex array. You bind it. That means it's the current one. And then you fill in all the state that you would normally have to fill in each time you wanted to draw. That includes the bind buffer. So now we're saying, hey, this is the active vertex buffer here. And then the GL enable attrib arrays and the attrib pointers are basically telling GL where your vertices are, where your normals are, if you had textures and colors, where those are. And then once we're done, we clear it out with a GL vertex array, a bind vertex array that's 0, do a bind buffer that's 0, and we're done. And then at the tear down here at the end, we're just deleting the things that we created. Okay, that was a lot to take in, but let's take a look at the draw, and maybe it'll start to make sense. In this draw and rect call, we're iterating over the SimpleGL objects, and again, all those are really doing is encapsulating the vertex array and the vertex buffer object. So we bind the vertex array object. And you might notice right before that, if we don't have a vertex array already created, we'll make one. The reason we do that here is that you can only make them on the thread you're using them. That'll be important later. So we bind the vertex array, we set up the effect, which basically just kind of fills in the shader information, and then we draw. And that's pretty much it. Okay, all that to just draw this single cube. Obviously not just to draw the single cube, we can also draw a whole bunch of cubes. So we just iterate through that call to create a cube 200 times, and voila, 200 cubes. So the question then is always, how far can we push it? So let's see if we can draw 10,000 cubes that way. And the first thing you might notice is that it's kind of slow. It's taken a while to do that. So that's the first tip off that something bad might be happening here. And if this was part of your app, then this is kind of a serious problem, because users don't really want to wait this long while you're trying to do something. So I tapped on it. It's creating 10,000 cubes. Okay, and here's the second problem. It's like, that's really slow. That's unacceptably slow. So we have a problem here. That's something we'll address next. All right, so after looking at that example, and I promise that's the longest chunk of code we'll look at, let's talk a little bit about the next part. So what was hard in that? I would say the syntax is definitely the hardest part. All those GL calls, GL vertex attribute pointer is a little illogical if you haven't been working with this stuff for a while. And it's true that GL draw arrays really does hate you personally. So once you set up everything and it just kind of crashes on you, then it can be hard to figure out why. What's also tricky is the data wrangling. So it's faster to draw fewer batches with more data than it is to draw more batches with fewer data, and that's a little non-intuitive. And the math, particularly for doing 3D, can be really tricky. There's a lot of linear algebra, particularly if you're doing 3D. But even if you're not, there's a fair bit of math there as well. So the best way to confront this is, buy some books. I would start there, do some web searching. These are a couple of books. The one on the left I actually used when I was switching to OpenGL ES 2.0 on iOS, and the one on the right I've heard good things about, and that's always a good place to start if you're into paper. There's also a lot of web resources. So for example, these are things that come up a lot when I'm looking for an explanation of something. The game community has some great resources for learning OpenGL ES, and GameDev.net had some good-looking tutorials. Ray Wenderlich's website has some nice tutorials. And if you're looking for random questions answered, you can't beat Stack Overflow for that. The standards body that handles OpenGL ES, Kronos, actually has a lot of good stuff, particularly reference documentation. And Apple, of course, they're the sample programs, the documentation. And I don't find the forums all that useful, but they can be useful sometimes. So looking at some of the game resources, when I went to put together this talk, I noticed that there was a talk on matrices and one on quaternions near the top of the GameDev.net webpage. So that's pretty cool. Those are things that would be extremely helpful if you're trying to learn some of the math behind 3D programming. Stack Overflow is always a great resource, and there are a lot of really interesting OpenGL ES questions there. You can just kind of surf those just to see what people might have been asking and how they answered it. But if you look at some of the top questions, particularly the top 20 or 30 questions, you'll see that one guy has been answering them for a couple of years. There was a period where he was answering a good chunk of them. And so his stuff's worth a look. That's Brad Larson, and he did some the iTunes U movies, which are interesting. They're a little bit old, but they're worth a look. He has a blog, which he hasn't updated much lately. And the big thing that he's done actually lately is GPUImage. And this is an image processing library based on OpenGL ES. And it works really well on iPhones and iPads. It's definitely worth a look if you're doing that sort of thing. But I also kind of like it just as a reference to see how you do crazy stuff in OpenGL ES. So definitely worth a look. Okay, so let's look at a slightly more complicated, at least from the geometry perspective, example. So we ended by looking at that 10,000 cubes example where we basically created 10,000 individual cubes with individual buffers one by one. And what we saw there was that, first of all, it took a long time to start up. So it would, if you had this in your own app, that would kind of be a problem. People would be impatient waiting for it to actually start up. And then the more important thing, I think, was that it's just really slow to draw. We're getting about 5 frames a second here. So that's not acceptable. So what do we do about that? Well, what we do is we can create the same 10,000 cubes with fewer buffers, and we get, in this case, we get about 30 frames a second. So that's pretty good, and that really shows how you should structure these things. And let's look at what we were doing there. All right, so obviously this view controller does a lot of other things. So let's look at the full example here and with all the various options. So there's that setup GL call here, and depending on the option that we're triggering, it's calling different setup routines. And the setup routine that we're interested in here is the second one, setup many cubes, few buffers. And this is setting up a whole bunch of cubes, but creating fewer flexi vertex buffers. And then basically the way it does this is you pass in the number of cubes to create, in this case 10,000, and we'll create a flexi vertex buffer to start. And then we'll start iterating through those cubes, and basically you just create a random cube called drand48, which will give you a number between 0 and 1 for the x, y, and z, and for the size. And then we'll just add that cube to the flexi vertex buffer. And then if we exceed a certain number of vertices, then we'll just flush it out. So we'll create that SimpleGL object, and then we'll add it to the array. And the reason we're doing asynchronized here is, I'll explain that later in a later example. And then once we've done that, we'll create a new flexi vertex buffer to fill in more data. And then at the end, if we still have data in our last vertex buffer, then we'll just flush that out. And then again, in our draw call, we're just iterating over those simple objects, binding them and drawing them. And then that works really, really well. So here we're creating a lot less buffers, and it's much faster. So pretty straightforward, and that's something you can do in general. You really want to batch this data to make it faster, and that's something you can do with GL. Essentially just put all your vertices together if you're drawing individual triangles, and you don't have to worry too much about how they're related, and basically make everything as uniform as possible. So if I had different colors on these, then I'd want to put a color on the vertex so that I could have vertices with different colors. Put textures together so you've got fewer state changes. There's just a general theme for how you want to make things fast, is make them uniform. And if we can even go up to 20,000 here, so now we're displaying 20,000 of these cubes, and it's still, at least on my device, still doing 30 frames a second. So that's quite good, and that really shows how you need to structure data with OpenGL. So in that last example, I wanted to show you how how instruments, which is one of the tools that Apple provides for analyzing what's going on with your app, how instruments would show you that in fact your batches were too small, that you were doing too many calls to draw with too little data. So here's what I recorded from that 10,000 boxes with 10,000 buffers example, and it didn't catch it actually, and I think that's a little bit interesting. It's not always reliable. It's always useful, instruments is, but it isn't necessarily going to catch everything. But I do highly recommend it when you're doing an OpenGL based app to actually run it, particularly with the analyzer, and see what you find. All right, so let's talk a little bit about open source toolkits. And this is definitely something worth a look if you're starting out on an OpenGL ES based project. Odds are that somebody has done it before, and maybe they did something that was worthwhile. So it's worth a look just to see. So here are some toolkits that I'm aware of. So if you're doing games, obviously, there's a lot of stuff out there, both free and not free. And Cocos 2D is one that people like quite a lot. I gather there's a 3D version as well. It's good. Apparently works pretty well. People use it. It's got shipping games if you're a gamer. One problem is I don't know how it's going to interact with SpriteKit, so that could be a little complex. Unity 3D is another one. Now, that's actually a commercial toolkit, but I think it has some sort of deal with free up to a certain point. I don't really know. I'm not a gamer. Lots of people use it, which is why I mentioned it. It's got a big community, a lot of tutorials, a lot of conferences. It's cross-platform. It's definitely worth a look if you're doing a game. So for just sort of general graphics, here's the toolkit. It's open, hence the name, and it's a scene graph. That's the other part of the name. And what a scene graph is basically just kind of a logical way of putting together 3D objects in memory. So you can have a group of them, and beneath the group you can have a transform, and then beneath the transform you can have geometry, and so on and so forth. It's a really logical way of putting things together. The only problem with that is it's also kind of a memory hog, so you got to be a little careful. However, OpenSceneGraph has been around for many years, and it's very mature, and it does some really complex stuff that's very, very hard to duplicate. It's C++, which might be a little complex if you haven't really dealt with it, but it's very, very good. So definitely worth a look if you're doing that sort of thing. There are also a lot of specialty toolkits, and I'm just going to talk about two of them here. I'd say if you need a toolkit that does something, just kind of go searching for it and see what you find. Obviously, I'm going to talk about mine, Whirly Globe Maply. That's the 3D mapping globe display toolkit that I make. And GPUImage is another one. I was going to show a quick example from GPUImage later in the talk. And that's a configurable shader-based image processing library, and it's very, very good and has some great examples. And again, there are tons of these things. Just kind of go looking for them, see if they've been updated lately, see what kind of state they're in, and give them a try. Now, although sort of in a different category, GLKit is also very useful and definitely worth a look. So this was the toolkit that Apple came out with to help with the 1.1 to 2.0 transition. That is when we were losing all that fixed functionality in OpenGL ES 1.1 and moving to 2.0 shaders. So they provided a lot of that fixed pipeline functionality in a 2.0 form. So there's things like the GLK view and the GLK view controller, and those are great for the setup and teardown logic, which can get a little complex when you're dealing with this stuff. There's also the texture loader, and if you've ever had to load textures yourself and get all the little pixels out and get them in the right format, this is really nice. Vector matrix and quaternion library, that's always good. And there's also GLK effects, and these are basically shaders and associated control logic. So they replace the matrix stack, they replace lighting, stuff like that. A lot of the stuff that was in 1.1. And this is good and definitely worth a look if you're just starting out, but just be aware that once you start having to do your own shaders, you're going to fall off a cliff. You can't really go from their effects to your own shaders without essentially losing their shaders. So just kind of factor that in, realize that at some point if you're doing anything even slightly complex, there's a good chance that you're going to have to rewrite all the stuff that you were using in their effects library. So that begs the question, if this is kind of complicated, why even do OpenGL ES yourself at all? There are these toolkits, so why not just use those? Well, the answer is, I mean, there are a bunch of answers. One is just that there isn't one toolkit to rule them all. Or really what's happened over the years is that there's been many one toolkits to rule them all. And none of them kind of does everything, and they're all, you know, in various states of repair, and, you know, people kind of kept writing them. And really, they end up being very specific toolkits for one domain or another. So there isn't one toolkit to rule them all. And if they're broad, it would probably cost you money. I also think you'll just learn a lot if you do straight OpenGL ES, and it'll improve how you use toolkits if you are using toolkits. Now, for this example, we're going to look at creating geometry dynamically. And there are a bunch of different reasons you might want to do this. Let's go back to this 20,000 cubes example. Now you might notice it starts up pretty fast, but there's a bit of a delay. And if we were doing anything tricky here in the startup, then the delay could get quite significant. So there are times that you really want to add the geometry after you're rendering in pieces. So let's look at doing that. So here we're adding the cubes about 3,000 at a time over, you know, spaced out about 1 second. So it may be a little hard to see in the recording, but basically it pauses every time you do that. So the main thread will pause while you're creating the geometry and adding it to GL. If you're doing anything complex, then you would really see it stop, just straight up stop. And even if it's not that complex, if you're dropping down, if your frame rate drops down, that can be very annoying to the user, particularly if they're interacting with the screen while this is happening. So it's something you want to avoid. And again, this is just adding geometry on the main thread, problem being that it'll pause while you're doing it. And there's nothing new here. I mean, we know this with UIKit, as you don't really want to do a lot of computation on the main thread because that's going to slow down UIKit and slow down your interface. So let's take a quick look at the example there where we're adding the geometry on the main thread. So again, it's a different setup call. Here we go, and it's add cubes every so often. And basically what we're doing here, let's look at the setup version, setup metered cubes here. We're calling it with the number of cubes to add, maybe about 3,000, and the number of times, which I think is about 8 or 9. And we're going to just run a perform selector with the add cubes every so often selector with the number of cubes and the number of times. And if you look at that add cubes every so often, it just basically calls setup many cubes few buffers, which is the optimized version of the setup cubes routine with the number of cubes. And then if it hasn't gotten down to 0, it just does another perform selector with a delay of 1 second. So it'll just add that number of cubes every second. Okay, so that's the example we're adding on the main thread. What if we want to do this on another thread? This is that version. This is setup multi-threaded metered cubes. And again, it takes the same arguments, the number of cubes to add and the number of times to add them. But here's where it deviates. It'll go and create another ELGL context. And remember, the EAGL context is where the GL calls are doing their thing. So the GL calls will look in the current thread, determine what the context is, and affect that context. So since we're going to have another thread, we can make another context. And there's this very convenient concept called a share group, which you'll see we're passing in as the second argument to that init call. And what this means is that if two contexts are in the same share group, they can share resources. And there's all sorts of restrictions on that. You got to be careful not to mess with the same resource in multiple threads. You have to be careful to create things like vertex arrays in the thread you're going to use them. And there's all sorts of stuff. But in general, it works pretty well. You have two contexts, they're in a common share group, you can share resources between them. And what that lets us do is what we're going to do here next. We're going to do a dispatch async using GCD, and that basically just creates a new thread. And in that thread, we're going to set our new context as that current context. And then we're just going to iterate through our setup many cubes, few buffers calls. So basically, every time this goes through, it sets up 3,000 cubes, then it sleeps for a second, then it does it again, and then it flushes out at the end. And then we're done. So that's basically it. In another thread, we are calling setup many cubes, few buffers, some number of times every second or so. And let's see again what that looks like. So it really works. It really works pretty well. We don't have any of that dropout in frame rate that you would see if you were doing this on the main thread. And you can also delete geometry, anything that's valid to do. In a GL context, you can do on another thread. You just have to make sure that if you're passing resources between, that you're not using them in multiple threads. And in fact, that's why we were doing, if we look in the draw call, that's why we're doing that at synchronized on the GL object. So every time we add 3,000 of these cubes, we add an entry to that GL objects array. Well, we have to call it at synchronized basically to set a lock on the array and make sure that we're not stomping on it in another thread. So in this draw routine, we have to do the same thing. We lock it, we draw, and then we unlock it. And that's basically all there is to it. All right, so after looking at that dynamic geometry example, let's take a look at a quick example of just how you can use some of the tools that Xcode provides. And this is just the performance display that Xcode has when you're running an app on your device, but you're tied to Xcode. So if you literally just compile the app as release, run it on the device, this is the display you'll get for an OpenGL ES based app. And I use this all the time. So this is great. It'll show you what your frames per second are. If you're aiming for 30, you can see I'm hitting 30 here on the top one. And it'll also show you some CPU and GPU utilization, which is a great hint as to what's going on in your app. So on the top, you see kind of where we ended. We're getting a nice steady 30 frames a second. We're not having big problems there. You can see on the right, the GPU's doing most of the work and the CPU's doing very little work. That's kind of where we want to be. And you can also get some hints about how the GPU is being utilized, which we won't really get into here. Look on the bottom and you can see that example of early on when we were drawing kind of smaller batches, what was going on. This is the case where we were drawing 10,000 boxes with 10,000 buffers, so very slow. And sure enough, we were getting 5 frames per second, as you can see in the upper right there. And the frame time is really suggestive as well. The CPU spending the bulk of the time and the GPU spending a little, so we're really underutilizing the GPU. So it gives you a good hint as to where you should be looking. Okay, so that was kind of a contrived example. It was boxes, and who's going to display that. Let's talk about a very similar example where we're doing much the same thing, where we need to do dynamic geometry replacement on the fly. And here's a case that's near and dear to my heart. It's tiled base maps. So what tiled base maps are basically you start with a map, and you start at level 0, and you make an image that maybe is 128 or 256 pixels on a side. That's level 0. You divide that up into 4 pieces. That's level 1. Each of those 4 pieces is the same size in pixels, and then you just keep going until you run out of disk space or you're kind of tired of it and you just stop. So you might get down to level 20, 21, something really deep. So obviously you can't load all this stuff at once. So what you do typically is you ask for a certain subset of these images from the server and you put them together like we see on the right, and that makes a picture. And it could be a flat a grid, or it could be a globe, but obviously globes are cooler, so let's just take a look at that example. Now here's an example where you would do a lot of geometry creation and destruction. This is an app called Mapbox Earth, and basically what it's doing is it's fetching small chunks of satellite data from the Mapbox servers, and it's creating the geometry to display them and then sticking them on top of the globe and drawing them. So as we zoom in, it'll fetch more data, and you can see the styles of the satellite data will change fairly radically as we get closer. So it's creating that geometry, slapping it down, and drawing it. So as we move around, it's doing all of that on a different thread. And of course, if you did that on the main thread, it would be very slow. So then you zoom back out again, it destroys all that geometry it created, and you're back to the top level globe. So this is a case where working on a thread other than the main thread is very important, and we create those GL resources on our construction thread and draw them on the main thread, and it works out quite well. And again, that app is called Mapbox Earth, and it's something you can get for free. And they've also open sourced that, although it's a fairly straightforward application of Whirly Globe Maply. Okay, so that was a good real-world example. Let's talk a little bit about how it worked. So again, we're talking about tiles here. Each individual texture is a tile. So when we ask for a tile and it comes back from the server, we want to add it. We could take the simple approach, which is to just create a texture for it, create some drawable geometry for it, point that drawable geometry at the texture, send it to the renderer, and then do that however many times, and we got ourselves a globe. If we want to get rid of a tile, we just reverse the process. It's pretty straightforward. But there are problems with that approach. Obviously, that's a lot of tiles. You're displaying something pretty big. It's going to result in a huge number of individual tiles. That's going to result in a lot of textures, a lot of drawable geometry. Too much state change is just going to be slow, kind of like for our box example. So what do you do about that? Well, there's two parts. The first part is what's known as a texture atlas, and this is where you take lots of little textures and you put them in one big texture. Now, gamers do this all the time, usually in a static way. They'll kind of put all their art assets in one big texture and then just index into that texture. We're doing it a little differently in that we have a dynamic texture atlas. We're putting images in and taking them back out as needed. But that's only half the problem. So the other way you solve this problem is with a drawable atlas. And this is just what we were doing in the example early on, when we were taking a whole bunch of boxes and just putting them together. So with the drawable atlas, you take all of your individual tiles and you put them in as few buffers as you can. And you put that together, and you've got your triangles pointing to your vertices, which are pointing into your texture atlas, and it works. You're just drawing a very small number of individual buffers, and OpenGL ES is very fast at that. So you say, okay, wonderful, that works. I see how you're doing that, but isn't this going to change as I move around? And sure enough, that's the case. As you scroll around a 2D map, or as you rotate that globe, it's going to change the contents of these buffers constantly. Now, if you were to do that on the main thread, that'll get really slow. So what I like to do is move everything off onto a construction thread. And this is kind of how I do things, but most people are doing something similar. So I've got a construction thread where we're doing all the requests to the remote server. We're building up the tiles as they come back. We're tearing them down when we no longer need them. And then once we set up all that geometry and set up those textures and downloaded it to OpenGL, then we tell the rendering thread to add it. So the rendering thread is doing very little actual work other than drawing. And then when we need to remove something, we do the same thing. We just ask the rendering thread to get rid of it. And sometimes the rendering thread needs to acknowledge that that's happened, because there are kind of these state transitions. We need to make sure we're not stepping on things. So there's a back and forth. But the main takeaway is that the rendering thread never really stops. It just kind of goes, it's doing its drawing at the right time. And it's the construction thread which is doing things that might take longer than a frame or aren't as predictable. All right, let's abruptly change tacks here and talk a little bit about another use for OpenGL ES. We've been looking at kind of standard 3D display stuff. It's got spheres and boxes, and it's pretty straightforward. But OpenGL ES can do a bunch of other stuff as well. It's very flexible, and this is one example. GPUImage is this toolkit for real-time image processing. It will do things like take camera input, take it frame by frame, run shaders on the results, and display the end of a processing chain. So how do you do it? Basically, Apple lets you get frames from the camera fairly quickly and do interesting things to them. AV Foundation is pretty flexible that way. A little bit arcane at times, but very flexible. The documentation is not super great for this kind of stuff, particularly if you want to transfer video frames into textures and maybe going back the other way. It gets a little wonky, but it does work really well. So you can also, I mean, that's part of it, is interfacing with AV Foundation and getting information out of the camera. You can also render to the texture rather than the screen. Like in all our examples, we're rendering our boxes to the screen, which is pretty standard. But you can also render to a buffer in memory and then use that buffer as a texture as input to another phase. And the syntax for that is a little bit weird, but it works in a really straightforward way once you get the hang of it. So you can put all this together and write custom filters as pixel shaders and chain them together, and you get yourself basically an image processing chain. So here's an example of an app that uses GPUImage, and let's take a look at the image filter that we have here. Now, what this is intended to be is basically an image filter that shows whatever the current camera input is as kind of an impressionist might see it. So there you can see the impressionist version of my bookcase. Very exciting. Basically, it's a collection of image filters, some of which are fairly standard. We're looking for edges, we're doing something with the edges, and then a couple of custom ones to go with it. And it's all implemented in individual shaders using the GPUImage library. And that's the kind of thing you can do with the GPUImage. It's got a lot of good examples, many of which are really sophisticated. So I glossed over a lot of the details there. How does the fast path from out of the camera work, for example? How do you set up rendering output to textures? And I'm going to just gloss over those. I recommend going to look at GPUImage, that library, to see how they did it. It's pretty nicely documented, and it's pretty logically constructed. When I need to do that sort of thing myself, I usually just go look at how they set it up. Now let's take a quick look at an example where we create a textured sphere, which is the kind of thing you might want to do with GeoData display. So here we've got a sphere made out of triangles, and there's a texture that we've laid over the top. It's obviously an earth texture. So this is actually fairly straightforward, so let's go look at the code. Let's start with a view controller here. And in our setup call, setup textured sphere, the first thing we're doing is looking for that texture. It's just a TIFF file that we've included in the resources for the project. And rather than loading it ourselves or creating it, we can actually call GL texture loader, which is really kind of nice if you've ever done all this work yourself for getting all the texels out and setting them up in GL. This is a much nicer way to do it. So once we've got that, then we create the Flexi Vertex Buffer and we add the sphere to it, and we'll look at that code next. And if we have a texture, we set up the various modes for it, what the color is going to be for the light, and other stuff related to the effect. So basically just say, hey, we would like to draw this texture on these objects. And then we create the GL object, which we're going to draw later, add it to the array. And remember that draw routine will actually just iterate through the list of GL objects and draw them. So let's take a look at the Flexi Vertex Buffer here. And this is like the add box call or the add cube call. It's adding a sphere at the given location with a given size. And this gets a little more complicated, but it's not too bad. Basically, the way this code works is it runs around from -180 longitude to +180 longitude, and from -90 latitude, basically the South Pole, to +90 latitude, the North Pole. And it samples vertices at each of those points, and then it just stores them away for later use. That's basically all that's going on here. So we keep track of those, and we also generate a texture coordinate so we can map a texture on the top, and the texture runs from -180 to +180 and -90 to +90. Pretty straightforward application. Not the best way of doing a sphere, but a really common one, something that you'll encounter a lot. And then once we've got those vertices, then we go through and create 2 triangles for each cell on the sphere. And there's a lot of code here, but all it's really doing is for each of those triangles appending a coordinate, a normal, and a texture coordinate. So there's 3 of those calls each, and it's doing 2 triangles, which results in a lot of calls. Obviously, if you were doing this for real, you could add some more routines to make this simpler. And then at last, it saves the vertex size here, which is, again, it's larger than it was before because it's 3 floats for the coordinates, 3 floats for the normals, and 2 floats for the texture coordinates. It sets has texture coordinates true, which is something that we introduced here. And then it also saves the number of vertices, and the number of vertices is basically 3 times the number of triangles, and we've got 2 triangles per cell, so that's what we're looking at there. And let's take a quick look at the SimpleGL object because we added some handling for the texture coordinates. And as I mentioned before, this is that make vertex array call. It's just setting up state for the vertex buffer, basically all the vertex attributes that you have to hook up to a shader, and you can go into that in glorious detail. But by adding the texture coordinates here, we have to hook up another set of information about the vertex. So that's what's going on here, where it says if has texture coordinates, then we need to enable that new array, the GLK vertex texture coordinate 0 array. And then we have to tell GL where it is. So it's basically offset by 24 bytes in each vertex. And there you go. And that results in a textured sphere. Well, that's pretty much it for the talk. Here's the standard resources. My toolkit can be found at that address. That's where the globe maply. GPUImage can be found at that GitHub address as well. Definitely worth a look. These slides can be found at that bit.ly address, and there's my contact info. So hopefully this was useful, and thanks for listening.